talking about products consisting of components, and components are made of material. So if we kind of think of it as an integrated system, rather than just seeing the product as sort of one component. So the principle basically talks about the fact that we can have the nutrients, which basically consist of product components and materials, going in two distinctive cycles. So the biological cycle is the one which will interact with the environment. So what we design to be circulating in this cycle consciously, so before we basically think of producing something, we think of a conscious design where there's a predefined and identified material pathway on how that material will circulate back to the economy. So the biological cycle basically will interact with the environment. If we design something to be biodegradable industrially or naturally, that'll go there. The technical cycle is a bit more robust. It can basically, it is the industrial environment where we can handle chemicals and a lot of the other things which are, which are not conducive to interact with the biological cycle. And that again, where we will identify pathways for products, components, and material to revive and regenerate at the time of design. So that's the basic principle that was basically introduced by Michael Braungart and William McDonough. But later, what we talk as circular economy evolved with the integration of a few other concepts as well. So this is the initial sort of diagram. If you kind of want to think of it as a set of strategies on how this can be implemented. So on the left-hand side is the biological cycle, where material can regenerate naturally or industrially. And on the right-hand side is are the strategies for the industrial cycle, where like there are basic 8 strategies that are being highlighted, some for products, some for components, and some for materials. So the whole idea is to keep firstly to regenerate, and to secondly to avoid waste and pollution, and thirdly to keep materials and products and components in use as much as possible. So I'll take an example to explain more. So I'm sorry that I don't have an example of the construction industry. I thought of taking the example as a washing machine. So in a linear economy, when we think of having buying a washing machine, we basically think of buying a washing machine, nothing else. So we purchase a washing machine, we use it for washing, and we think of disposing it. So that's what we are doing mostly now. In a circular economy, we don't think of a washing machine as a washing machine. We think of 2 things. Firstly, we think of it as a product which has been manufactured with a certain resource footprint and an environmental footprint. So basically, once it is manufactured, we try to keep using it for longer, or to use another set of strategies basically to get the maximum out of what has been produced. And secondly, we don't think of it as a product that we should buy and own. We think of what is the fundamental human need that is fulfilled with the washing machine. So we use it for basically washing clothes. So rather than basically buying the washing machine, if we can use it, if we can have another systematic mechanism, a mechanism which kind of operates within a system where we can get the service of washing clothes rather than owning the material and disposing the material, that is what we would encourage in a circular economy. So coming back to the 8 strategies, the first 4 strategies are about keeping the product intact and as it is, and keeping it longer in use. So can we basically have a washing machine, if it is produced, can we have more people sharing it? Can we provide more access to, rather than one person owning it and using it, can we provide access to more people? Then secondly, can we maintain the services of it? Which means rather than a manufacturer basically selling the washing machine to one party, can we basically sell the services of the washing machine to multiple parties, with the manufacturer keeping the ownership? So basically you can sell washers, cycle of washers. You can sell the washing machine services by hiring it for a certain period. The core idea that is being addressed here is that the information of a product that needs to be used, or that is useful for end of life management of a product, if it is passed on to a consumer who actually don't know how to use that product, that information is lost. So if the ownership of the product is maintained with a manufacturer who has access to the vertical supply chain of manufacturing of the product, as well as the access to the repair and the information to basically keep the product longer in use, that is a preferred method of managing a product. So rather than basically owning things, we we encourage the products, components, and material to run in a system, and we as humans, we access the system to get the services of it. So that's what number 2 is about. And number 3 and number 4 are about it has already been manufactured. Can we basically have a secondary market where there's more people getting access to the product? Number 4 is about, can we basically sell repair services with the product, so that there's guaranteed sort of repairs to keep it for a longer time in use. And once the product level strategies are explored, we then come to think of what can be done with the components. So if the washing machine is designed with some components which can be kept longer in use. For example, if you see the top cover, if it's made of hard plastic, it has a really long life and a long durability. So rather than when one part fails, if we design for the disassembly, can we replace some of the parts, remanufacture them, refurbish them, and then still have the product kept in use? And number 7 and 8 are material related strategies. So upcycling is, if I take an example again, if you think of the top cover of the washing machine, if you know that it's hard plastic, and at the end of its life, either you can use it to manufacture hard plastic, or if you think, look, it can be used to manufacture a plastic chair, then at the time of designing the material, you design it to make it easy to manufacture a chair. So basically, upcycling is identifying a use prior, so that the material can be diverted to the best value use. And the last one, of course, is recycling it as a commodity. So these are some of the strategies that we practice in a circular economy, so that we can basically, with economic activities being performed when we consume services and goods, we, rather than creating a footprint which is a resource footprint and an energy footprint which is harmful or degenerating, we can basically think of sending the material back to the economy as much as possible. And of course, use of renewable energy is very much encouraged in a circular economy, because it fossil fuel related energy, of course, has a resource footprint as well. So I probably wanted to give you an idea of what circular economy is about. So to come back to the topic, if we think of what needs to be done and what is happening now, and how do we make transition from a linear to a circular economy. So the first part was very conceptual. We are coming more and more into the practice parts now. So being in a linear economy, when we think of running with it towards a circular economy, we are in a position like this. We have to sort of move forward, but we are sort of not equipped with the right tools. So what would happen in a situation like this, that we will continuously basically extract resources. We have economic activities performed with it, and we have waste generated, and we'll have increased amount of resources and energy spent on recycling waste to basically recover it. And what needs to happen is that increasingly we need to develop what we call alternatives. So alternatives are new ways of sort of replacing the current way of doing things, and more we would be replacing them with what we are currently doing, and then that only probably gives us a smooth ride. So this is a very long journey. It's very easy to talk about it conceptually, but it's a really sort of a long and a long-term journey to get there. And if I think of it from a sort of a more implementation point of view, the alternatives developed, for a circular economy, we can broadly categorize into alternative products that are in line with circular economy principles, alternative materials, alternative supply chains, and alternative business models. And when these alternatives are developed, we would need a mechanism to measure them against what is being practiced today, which we can call as the traditional way of doing things, or the base case. So the tools to measure, businesses and industries will measure them in a different way. Public authorities or government as a policymaker, or a sort of a organizations who work on wider public interest, will measure them in a different way. And thirdly, we want people to uptake them, or we want organizations to basically implement them. So implementation will require designing new value chains, and then creating reasons to basically uptake, which sometimes would involve incentives and disincentives to move into a new model. And fourth, we will need, so a new economy developing sort of new materials, there'll be new consumption choices that needs to be introduced. So basically there's there are new markets created where buyer behavior needs to be understood, new consumption choices, and behavioral change management in terms of consumption needs to be introduced. So these are like, once again, high level sort of strategies. If you think of like basic sort of 4 steps that we require to implement alternatives towards a circular economy. So the area that I mostly, I put a chicken and egg to ask what should come first. Should the alternatives comes first and then we think of number 2, 3, and 4? Or we think of what the alternative would look like, and we already work on getting 2, 3, and 4 ready. So is it a question of chicken or egg? What should come first? Can we wait for the first one to come and then work on the next couple of things? So the 2, 3, and 4 are the areas that I primarily work on my research, basically enabling alternatives for a circular economy. And I have 3 main projects currently going in these 3 areas. And what I will share with you is a project completed on the first one, basically measuring alternatives towards a circular economy for public policy decisions. So that is the what we have done here is basically the alternative number 1 has not been fully developed. So there's an alternative use of material, use of an alternative sustainable material in a product. The sustainable alternative material is recycled concrete aggregate, which is a product of demolished concrete. The research is currently ongoing on basically advancing the ways of replacing it, creating new mixed designs, and creating new ways of manufacturing, creating new ways of aggregate conditioning. The research is still advancing. There have been a number of applications and tests being done. There are new research findings on product performance, durability, mechanical performance. It's still happening. So what I've done there is basically, when one is happening, one is sort of still underway, taking the learnings from it at a certain point of time and develop a sort of an industrial model so that the number 2 can be performed to evaluate where it stands. So that's the example that I'm taking to explain what has been done in that. So I think we can go to the example. So this is the first project that I'm sharing with you. I can probably talk about the second project very briefly based on how we have time. So I will go ahead. So it's not going forward. Yeah. So the case study is, as I said, is on the use of recycled concrete aggregate, which means the crushed product from demolished concrete, the coarse portion of that in concrete. So to give a bit of background and context about why this is explored as an alternative. So concrete is the highest consumed man-made material on Earth. We have a very significant production of concrete happening every year. And with that, there's when concrete structures made with concrete reach end of life, there's a significant amount of concrete waste generated. And on the other hand, we, being in a linear economy, we also have quite a bit of natural aggregate that we require for production of concrete. So if I analyze the current context of Australia, out of 10 to 15% of the total waste generated is concrete waste. And in Australia, the statistic, and probably in the last, this relates to the last 5 years of measurements, about 45% was going to landfill, 55% was recycled. And almost all what was recycled is used as a road-based material. Now, what is landfill is basically a resource going to waste. It's an environmental liability at the same time. And what is used as a road-based material, it's a good alternative use, but it's what we call downcycling. Downcycling is basically we are not realizing the best value of the material for the next the application in a next life, because recycled concrete aggregate has concrete as a constituent material, which is a very highly energy intensive product, and it has better capabilities for use in the secondary life, and that being used as a road-based material replacing rock is basically a downcycling use. So if we think of what can be done, so as is, we produce, now this is I'm talking about now the alternative use. So currently we mine natural aggregate rock, which is quarried and processed, and it produces natural coarse aggregate. So I'm only taking the coarse aggregate, not the fine aggregate, which will be mixed with other constituent materials, which includes fine aggregate, as we call sand in Sri Lanka, cement, other cementitious materials, chemical additives, mineral additives, and water. We have ready-mix concrete manufacturing to produce, in this project, I call it as natural aggregate concrete. So this is a typical concrete we produce in a ready-mix concrete facility. So I quickly want to explain about the market in Australia. So in Sri Lanka, we have the practice where we have mixing of concrete happening on site, especially for residential construction. But in Australia, that hardly happens. Most of the concrete that is used in structures are coming from ready-mix concrete manufacturing facilities. So the to-be case, this is the traditional way of doing things. The to-be case would be that we will have waste concrete subject to crushing, which will be producing a mixed material like that, something with brick, mortar, coarse aggregate, fines, dust, everything. So if we get the coarse aggregate portion of it, so separating it out, if we have particles higher than generally 5 millimeters taken out, and we have an aggregate product containing residual mortar, and if we can partially replace it in the ready-mix concrete manufacturing facility to produce recycled aggregate, produce ready-mix concrete, and that concrete in this study I have called it as recycled aggregate concrete. So I'm using these two terms intermittently. RCA stands for recycled concrete aggregate, which is the aggregate product. RAC stands for the concrete product, which is made by partially replacing this in a ready-mix manufacturing process. So this is basically the traditional case, and this is the alternative that we are talking about. So if we generally think of the alternative, again, I'm still in the background trying to understand why we should be doing it. So in the context of Australia, if we have, if there's a need to find a destination, a destination which is which we can consider as environmentally responsible for construction and demolition waste. So other developed countries like Japan or some European countries, they have achieved very high recycling rates by the mid-1990s. In Australia, as a developed country, it was the percentage of recycling was still very low. And on the other hand, sorry, can I go ahead? Did someone ask a question?
No, ma'am, you can go ahead.
Yeah. So if you think of natural aggregate, we need natural aggregate for construction. And the more and more the urban quarries are getting exploited, we have to transport material from distant quarries. So basically the energy for bringing the natural aggregate also gets higher, and it's not increasing in a linear fashion, it's increasing exponentially. More and more the natural aggregate is sort of getting consumed. So basically there's the having recycled concrete aggregate used in concrete, structural concrete, it seems a very rational choice to basically consider. So what is basically delaying basically not carrying out the initiative? So in general, if you think of the material performance of recycled aggregate concrete as a product, if we use RCA, which is recycled concrete aggregate, the aggregate product is considered weaker or to have inferior quality. This is actually a perception. I would not like to sort of comment on it technically at the moment. I'll talk a bit more about it when we talk about the mixed designs. But in general, it's considered as an inferior material or a material with a less than standard quality. So when concrete is manufactured with RCA, does it mean that the concrete product actually is a not considered a superior product? So the reason for not using it, is it actually a problem with material performance? So there's a question about it, which is 100% not answered. Then when we use recycled concrete aggregate in concrete, there are some mixed design techniques which adopt higher use of a high percentage of cement in the mixed design. So basically, we are having compensating techniques to adopt a recycled material, and does that basically increase the cost of the material? So is it actually more expensive to do it? Then thirdly, so production of, there's a way that recycled concrete aggregate is produced by recycling. There's a way that natural aggregate is produced, which is aggregate crushing, rock crushing. So is this a more environmentally sound product? So basically, can we justify the use of recycled concrete aggregate from an environmental perspective? Does it have a good environmental case to justify that? So these couple of questions are vaguely answered or not 100% or answered in an integrated way. So basically, the case to use recycled concrete aggregate in concrete, whether it can be justified with a good business case or with a sound environmental case, was a question that was not answered in general. So that I mean, at the time that I started the study, I thought that was one of the reasons where the industry uptake was was low or was happening only at trial scale. So what we have here is a complex problem which require multiple criteria for evaluation, and we want a representative result to compare. So if we basically think of ourselves as a government, if we are to encourage this alternative, we need some basis to think that, look, encouraging recycled concrete aggregate is a good thing to do. And how do we judge that? The governments usually take decisions considering the benefit to society. So how can we basically think or measure whether doing this is the way to go? So the criteria that was used for this study, it was based on principles of sustainability and financial viability of the end product, because whatever gets implemented needs to have a good business case as well. So there's a need to have a framework integrating all dimensions. So what I used here for this study was cost benefit analysis. And what cost benefit, with cost benefit analysis, what was derived was an indicator called net present value. I'll talk a bit more about the net present value in the next couple of slides. So what was done is basically there's a problem where there are multiple things that needed to be considered in coming up with one representative answer, and the technique basically was used to address that problem and bring that answer together to give a representative result. So I also thought to briefly touch upon, based on, before I share the results of the study, briefly touch upon other multi-criteria decision methods that can be used. So I simply took the examples of apples and oranges. So that's usually what we get to compare in different decisions. So apples and oranges basically represent that you are dealing with different things to compare in making integrated decisions for policy decisions. Now, for example, cost-benefit analysis. So if I take an example for Apple could be environmental impact. Oranges could be material performance. And then Z is a monetary value. So basically, we, in a cost-benefit analysis, what we do is we convert everything to money value. So apples are converted to money, oranges are converted to money. Z you anyway have, third one you anyway have as money. And in cost-benefit analysis, we basically, even though I have put it as added, we integrate it. Sometimes it's added, sometimes it needs adjustments in adding. It's simply not just 1 + 1 + 2. But what we do is basically in cost-benefit analysis, integrate apples, oranges, and money into one indicator, which is money. One of the other techniques we can use is called cost-effective analysis. So in cost-effective analysis, again, we have apples, oranges, and money. And the result is basically a ratio. So we basically check how effective one indicator can be when we compare in comparison with the effect of money. So if we think of effectiveness of apples as a ratio of money, or effectiveness of oranges as a ratio of money. So basically environmental impact divided by cost, or performance divided by cost. So here we get ratios which we use as indicators to govern our decision. But you get more than one indicator. With cost-benefit analysis, you get only one indicator. There's another technique, a couple of other techniques, but just took an example. It's called multi-criteria decision analysis. So here we recognize the answer from different criteria as is. So apples will give apples, oranges will give oranges, money will give money. And we use something as we call a relative performance indicator matrix to decide on what is best. So the result is basically based on what is relatively important. If in a decision you say apples are more important, we allocate higher relative importance on apples in the decision. So then the decision will give a result which is more favorable to having apples as the main thing. So it's basically the decision analysis, or the decision process is favoring what we define as what is important for us at the beginning of decision making. So here again, we look at three things differently and make a decision. So what I gave you was basically an overview of how decisions are made in a context where there are more than one criteria which should govern the decision. So in this study, I have taken cost-benefit analysis, and I'll again jump into the example. So what I did in this study was to evaluate the use of recycled concrete aggregate in structural concrete, replacing natural aggregate. Why it was done? Because we need a representative result combining multiple indicators or multiple aspects. And in this study, there was in some cases there were methods developed and basically an evaluation performed to come up with that representative indicator. And before I forget, I probably will share with you at the end, but this is a study that I actually conducted for my PhD. So I told that I would come back to explain what NPV is about. So NPV usually stands for net present value. An NPV used for this cost-benefit analysis is not is an economic indicator. It's not purely a financial indicator. It measures is an absolute indicator which measures monetary value considering time value of money. So if I briefly compare economic and financial analysis, in financial analysis, we talk about profit, which is revenue minus costs. But in economic analysis, we talk about benefits minus costs. So benefits are wider benefits to society. In financial analysis, we have a number calculated associated with a single party. So it could be the profit for the construction contractor. But in economic analysis, we analyze it based on benefit to society. So the principal stakeholder is society or the public. And financial analysis only captured what we call as internalized items, which means items which already have a price for. Whereas economic analysis captures what we call externalities. If we think of things like pollution, carbon dioxide emissions, degradation of soil quality. So if you can assign economic value to it, we can basically capture that through an economic analysis. So in this study, what I have calculated is the net present value, which is the financial cost or cost saving if the external cost of doing it or not doing it is incorporated into the financial cost. So imagine that there are monetary values associated with things like pollution, or not extracting aggregate, or not sending waste to landfill. If you add that monetary value and incorporate that into the current financial system, would that initiative be favorable? So that is what I have been measuring. So it's important to understand why this is needed. So if in the financial analysis, if the cost of recycled aggregate concrete is higher than the cost of natural aggregate concrete, unless this can be passed as a price to the customers, the commercial sector would not produce it. But if the economic analysis gives the result that recycled aggregate concrete has a higher benefit to society than natural aggregate concrete, then society benefits with production. So basically, then to initiate production, the polluters need to pay. Basically, the one who commits externalities will need to pay and pass it to the ones avoiding pollution. So in a country, typically government or the public sector is the one which would undertake this regulatory action. So what we are doing is basically empowering them with them information on taking such a decision. So the framework that I used is this. It has a number of steps. I will try to explain it as briefly as possible. So there's the first part, which was a technical assessment. The second part where, in the first part, what was done was to simulate the entire industrial system. If a product called recycled concrete aggregate is produced, which can be used as a constituent material in concrete by the ready-mix concrete industry, how would that production setup be? So simulating that production environment was the first part of the study. And then based on that system, financial effect of that was estimated. Embodied energy or the environmental emissions emissions with energy consumption was estimated. Then I also estimate this one. I'll not talk about it much because it takes time. The fourth one and the main one was the indirect environmental impact. So the monetized benefit of not sending waste to landfill and the monetized benefit of not extracting natural aggregate. So that those two together form what we call as the total external cost or benefit to society. That integrated with the financial cost of production provided the net present value of a unit volume of recycled aggregate against natural aggregate concrete. So this was like the total framework used for the study. Can I quickly stop and ask Sitamini how much time I have got? Is it 10 minutes?
15 minutes, ma'am. We can continue.
Okay. Alrighty. So I can decide on the level of detail I can go to. So so I'll probably explain very quickly how the technical assessment, the thinking behind is or the principles that was used. So again, it's about simulating what the production environment will be for a new alternative. So if there's a recycled concrete aggregate produced to be used in ready-mix concrete production, how will the demolition operation change? How will recycling change? How will concrete production mix change? And how will the ready-mix concrete manufacturing setup change? So those changes were basically captured in different scenarios. So in this study, what I've assumed is there's appropriate refinement than complete refinement, which means when you basically crush waste concrete, you could crush it and clean it and wash it, and you could basically make it as close as possible to the natural aggregate. But by doing that, you're consuming, you are spending money, you're basically having costs as well as having more energy requirements. So rather than achieving a purity in the material, I was focusing more on practically crushing it and separating it with a very simple separating mechanism. Then secondly, as much as possible using the current industrial setup. So it was not about designing new machinery or new equipment. Using the existing recycling manufacturing facilities and existing ready-mix concrete manufacturing facilities and doing incremental changes to those, and basically having this implemented. So those were like two assumptions that were considered. Now, if you think of the mix design, that how the mix design should change, you need to consider that recycled concrete aggregate was a different material to natural aggregate. It has attached residual mortar, it has micro cracks, it's porous, inhomogeneous. So basically there's more contamination in the material. The quality of the material is varying compared to natural aggregate. Also because of residual mortar, it has high water absorption. So the current Australian guideline was specifying to use it for less than 40 MPa, 40 megapascal strength, at 30% replacement scenario. So that was also a recycled concrete aggregate complying with a certain quality standard. So with this one, you need to basically conduct experiments. So I did some preliminary experiments during my research, but at the same time, I probably referred to approximately 70 to 80 papers to understand how application performance have been established by other researchers. So rather than basically relying on the work that I had, it was more to reinforce what I have read. But I mostly relied on the current literature published on experiments conducted already. So with that, the mix design needed to change. So basically, for the mix design, there was a need to add to have the variability accounted for. You needed to basically increase the safety factors like the target mean strength, etc. You need to have a higher plasticizer to reduce some impacts due to high water absorption, supplementary material addition, because that was discussed in literature that having fine supplementary cementitious material improve quality. So there were a few mixed scenarios that were simulated based on the published work. Now, coming to the industrial setup, I probably visited the 10 industrial plants in Melbourne at the time. There were 3 types of plants that you could basically see in terms of the level of automation that they have. So there was something called front-end loader, hybrid, and overhead bin. So overhead bin had the highest level of automation. So if you think of introducing new storage and to handle a new material called recycled concrete aggregate, new feeding lines, new mixing mechanisms, these 3 types of plants had to react in a different way to have a new material coming in. So that was what I needed to assess to conduct especially capital intensive modifications required. So as a summary, if for changes in the manufacturing environment, I assume that we use the current recycling process. Fine aggregate and coarse aggregate was separated using a simple sieving process. Quality control, an integrated quality control system had to be introduced. So there are multiple quality control points, as well as additional costs accounted for additional quality control operations. And I assume that these 3 types of plants with different degrees of automation will basically manufacture this product called recycled aggregate concrete. In terms of mix, so this produced basically 3 manufacturing scenarios for these 3 plants. Then changes to the mix, there were 3 strength categories analyzed, different rates of replacement of recycled concrete aggregate, and mix scenarios 1, 2, and 3. So these were about how plasticizer content or supplementary cementitious material or any other sort of mixed constituents changed to come up with a product which is equivalent to natural aggregate concrete product. So this probably gave another 36 different mixers, and this gave 3 manufacturing variations. So these were the scenarios that were used to model that system. Now, with that, we kind of have the model was developed using MATLAB and Excel, like an integrated model. So next was to basically perform the different types of assessments. So financial assessment was about mapping where would the cost increase. So the techniques that were needed were process costing, activity-based costing, and incremental costing. So this was basically the cost structure. I would not try to explain it. These were the plants considered. If I summarize this very briefly, the material cost of the product was, there's a unit incremental cost. Basically, the natural aggregate concrete product cost was increasing because the material, I would say not increasing, the change to the natural aggregate concrete price due to the increase of material cost and due to the increase of processing cost. So those were mapped based on what is being changed in the model to come up with the final price of recycled aggregate concrete if it is manufactured using this setup. The next step was to conduct an embodied energy assessment, which again, based on the same manufacturing setup, and I used a method called input-output based hybrid method for analyzing the embodied energy. The third and the most difficult and the most complex one was the indirect environmental impact assessment. So there are a number of methods that you can use, which are economic evaluation methods, to basically monetize the externalities. So I used one of the simplest techniques, which is called benefit transfer and adjusted transfer method. So what I monetized here was the cost of not extracting natural aggregate from a quarry, and also not sending concrete construction and demolition waste to landfill. So the figures for those were estimated using these two methods. So, most of the work was based on published literature and making relevant adjustments to Australia and making relevant adjustments to the quarrying and like other conditions which we can expect to be observed in Australia. So the work was published in 6 papers, different studies for each of them. I'll just share the results of the study. The financial assessment basically provided the answer that alternative is expensive to manufacture. So different manufacturing plants have different type of cost responses. Highly automated plants had a higher, overhead bin was the highly automated plant. It had a higher cost in terms of manufacturing because they have additional feeding lines, additional storage, a lot of sort of additional things to be incorporated with the introduction of a new material. So the cost was approximately 2.5 to 10% higher. So this was basically calculated based on Monte Carlo simulation. It's a probabilistic estimation. The price of recycled aggregate concrete, if it was manufactured, was 2.5 to 10% higher. Embodied energy gave an interesting answer. It was very similar. So basically the emissions associated with the crushing of concrete and natural aggregate extraction was quite similar. Because of that, the embodied energy was plus or minus for different scenarios. Effect of carbonation, this is the ability of concrete to absorb carbon dioxide, it was very minor. Indirect impact gave the highest difference. So if you monetize the cost of diversion of waste from landfill and damage avoidance due to natural aggregate quarrying, this is including the impact on biodiversity, noise pollution, and all of that, that gave an answer which kind of flipped the picture. So basically, what finally happened was that what I initially sort of showed, initially presented to you, it was expensive to produce by the private sector, but when you incorporate the net benefit of all the external costs, the net present value of recycled aggregate concrete was 4.2 to 6%. Net benefit was 4.2 to 6.6% at 30% replacement of recycled aggregate concrete. So basically the society benefits with its production, and if you pass on the external cost to the as a as a cost saving to the price, recycled aggregate concrete would be cheaper. So that's what the answer gave finally. I also extended the analysis to incorporating that in a building, which I might not have time to share with you. So I'll basically skip on to the next ones. So what it provided basically was an idea of what are the barriers in the value chain to get some of these alternatives up and running. So if you think of what needs to be done, so basically it's the external cost basically provides the key to makes the picture complete, so that when the external cost is incorporated into the pricing, the price gets lower. So basically, to recognize the external cost, one of the things that can be done is introducing pricing or tax on quarrying, which basically disincentivizes quarrying, or taxing the landfill so that landfilling becomes expensive. There's more material going in the other direction, or subsidize recycling. By introducing a subsidy, you encourage recycling, or providing incentives for more and more concrete manufacturers to use recycled concrete rather than recycled concrete aggregate rather than natural aggregate. On the other hand, you can also incentivize this by incentivizing the product. So higher points in the green building system for using alternative materials such as this. So this provides basically system of incentives and disincentives that you can adopt to get such an alternative going. But these interventions are very much needed by public authorities. So that's why the market itself does not correct that. So there are interventions needed from the economy to get that happening. So it's basically a carrot and stick approach. You have a carrot to encourage something and a stick to penalize something. So the work, as I said again, was a work of during my PhD, and there were overall research framework. My main supervisor was Professor Priyan Mendis, and Dimitris is an economist. So there were different skills from different people who contributed to the study. Some were engineers, some were environmental scientists, some were economists, and Dimitris and Professor Priyan are economists basically. And I basically, so where's myself? I was basically relying on my knowledge on financial assessment and supply chain design. So there was a team of different people with different skills who contributed to the study as a whole, who also became co-authors of publications. And I also got data from different recycling companies, demolition contractors, landfill operators, quantity surveyors, and the study was basically mostly used based on real-life data. So I would not have time to talk a lot about the other two projects, but I'll give a basic introduction to this one to tell what findings of such a study, Project 1, can lead to then afterwards. So this is a study that we are doing with by introducing another simulation tool. Where I'm working with another colleague who's an expert in systems and controls and predictive modeling, and we have a PhD student who we supervise together. And that one once again comes to this diagram and the framework. What do we need to do to create incentives or disincentives for something that does not get corrected by the market? So what we do there is basically thinking of an industry structure, and if you think of one like a recycled product coming, there's recycling happening. The material from the recycling operation, there could be multiple material streams, and they're going into different products. So basically, the material is going to a secondary market. So we are doing a study on what would happen if different policy instruments are introduced. So instruments could be regulatory instruments like controls, like banning, which completely stops a certain material flow, imposing a minimum or maximum quota, which means you limit the quantities by having an upper boundary or a lower boundary, or it could be pricing instruments, which could be taxes or subsidies. So we basically use market dynamics based on theories of microeconomics in the model and equilibrium control. So basically markets will need to come to an equilibrium for us to test the model. It's based on controllers. So there's a market, recycling material markets, which we use as the base case. And then we have a policy goal and we introduce an instrument. So instrument could be a ban, a limit, a tax, or a subsidy. That instrument will need to help achieve this policy goal. So with the introduction of the instrument, it introduces disturbance on the system and the market will come to a new equilibrium. And then we assess the effectiveness of the instrument to achieve the policy goal. So that is a sort of another simulation and modeling that we do to assess the effectiveness of some of those instruments in achieving the policy goals. So for these studies, we are in discussion with the Victorian government, so to check whether we can sort of work with them on some things. And I think that's probably the time that I have to present action. And thank you, Green Building Council, for having me. It's a pleasure to talk to an audience in Sri Lanka. So the topic today is policy decisions in the construction industry, evaluating alternatives towards a circular economy. I hope all of you can see my screen. So I will go ahead with the presentation then. Yeah, so because most of the people who attend the session today are from the construction industry and also like related building material in other industries, I thought I'll take a few slides or rather a few minutes in the session to talk about what a circular economy is. So I want to sort of give an introduction so that everybody's on the same page when we talk about the alternatives towards a circular economy. So the easiest way to sort of describe it is to basically describe what we are in right now. So we call the current economy that we are in now as a more linear economy, where it's an extractive economy and it's a degenerative industrial model. So when we talk about an economy, we mainly talk about three main activities, three key economic activities, which is production, distribution, and consumption. So everything that happens in an economy can generally be very, very broadly categorized into like these three activities, and that's the purpose of an economy operating. So in a linear economy, when production, distribution, and consumption happens, we have extraction happening to produce, and at the same time, during production and distribution, we emit energy, and at the end of consumption, we have waste. So basically, from at the very beginning and at the very end, we have resource degeneration happening, and then during production and distribution, as well as sometimes consumption, we have an extensive amount of energy being required. So from this model to a new model where with economic activity, the environmental does not degrade economic activity, or we have economic activity increasing, that has a negative impact on the environment. The model that we want to go towards is when we want to increase economic activity or increase consumption, the degeneration of the environment is minimal, and if possible, regeneration happens. So how is that possible? So if I go back and touch base on the definition of a circular economy, it's an alternative economic model that focuses on regeneration of products, components, and materials to the highest utility and value. So I'll probably explain a bit more in the next couple of slides. Sorry. Sorry. So where does the thinking actually start? So probably in the last 2 to 3 decades, the concept of circular economy has been widely discussed. And one of the two thought leaders who introduced the concept initially are Michael Braungart, a German chemist, and an American designer and architect called William McDonough. So they talked about the fact that every time that we we have products being produced and services being used. We shouldn't basically just limit ourselves to being sustainable. So basically avoiding the negative impact. We should go beyond that and think whether we can do good to the environment. So less bad is not good. That was one of their main mottos in talking about this principle. So their principle goes as cradle to cradle principle, and what it does is basically distinctively identify two cycles where materials can circulate. So on the right hand side, I have a sort of a watch. It's if we call it a product, it's made of components, and the components are made of materials.